Everyone, welcome back. This is lecture 7 of the lecture series Signals and Systems. In the previous lecture, we saw about the historical perspective of Fourier analysis, in which continuous time periodic signals can be represented using periodic complex exponentials. We also saw the response of LTI systems to complex exponential and actually observed that the complex exponential are nothing but the eigenfunctions of the LTI systems, which in turn makes them as a useful class of signals. In this lecture, we will see the Fourier series representation of continuous time periodic signals and also discuss about the convergence of Fourier series and Dirichlet conditions. So, let's get started. So, we all know what is a periodic signal. A signal x of t is said to be periodic if x of t is equal to x of t plus capital T for all t and for t non equal to 0 and finite. And we define the fundamental period to be the minimum such t. Minimum such t and which is positive and non-zero, right? We can also define the fundamental frequency represented by omega naught to be 2 pi by t, given that t is the fundamental period, or let us say it is t naught. So t naught is fundamental period. Then we also have the complex periodic exponential given by e power j omega naught. So this is the complex exponential. And this is again periodic with fundamental frequency omega naught, right? And we also have sinusoidal signals like cosine and sine. So sine omega naught t or cos omega naught t. These are also again periodic with fundamental frequency of omega naught. And we also saw how these are related. For instance, sine omega naught t is nothing but e power j omega naught t minus e power minus j omega naught t by 2j. And cos omega naught t is nothing but e power j omega naught t plus e power minus j omega naught t by 2. And we can also write the fundamental, we can also say this omega naught as a fundamental component e power j omega naught t, and we have a set of harmonically related component. So these are nothing but e power j k omega naught t, and k can belong to integers 0 plus minus 1 plus minus 2 and so on. So this are nothing but having fundamental frequency of k omega naught. So we can also say it is also periodic with period t naught. So it is actually periodic with period t naught by k, which implies that it is also periodic for t naught, right? Because k is an integer. So we'll just represent it as some phi k of t, e power j k omega naught t, and k can be 0 plus minus 1 plus minus 2 and so on. So now if we just sum up these, giving them some coefficient ak e power j k omega naught t, and we sum it, let's say, from infinity to minus infinity to infinity. So this is again should be periodic. And what will be the period? With period t or t naught, right? Because each of these components are periodic with period t naught, and when you sum them up, it also should be periodic with period t naught. And these terms for k equal to 1, they are referred to as fundamental component or first harmonic. For k equal to 2, they are referred to as second harmonic, and so on. Now, on this, if we apply the constraint that x of t is real, then what do we have? We have x of t is equal to x star of t, right? The complex conjugate. So then x of t is same, minus infinity to infinity, ak e power j k omega naught t, and this is equal to summation k equal to minus infinity to infinity x star. You will get ak star e power minus j k omega naught t, right? Because e power j k omega naught t is nothing but cos k omega naught t plus j sin k omega naught t. So complex conjugate of this will be nothing but e power minus j k omega naught t. T minus j sin k omega naught t. So now let us try to relate the coefficients. So if we just try to keep this same and then try to relate, then it is just replacing k with minus k. So the summation will actually go from infinity to minus infinity. But since it is a summation, it doesn't matter if we count from first to last or last to first. So we can keep this same. Minus infinity to infinity. This k will change to minus k. And we'll have e power j k omega naught t. And on the left hand side, we have ak e power j k omega naught t. And what we observe is ak is actually equal to a minus k star, or in other words, a minus k is equal to a k star, just taking complex conjugate on both sides. So you will get a k star here, a minus k here, right, which implies that a minus k is equal to a k star. So now if we try to substitute this in the initial equation, so we have x of t is equal to summation k equal to minus infinity to infinity ak e power j k omega naught t. Let's combine the positive and negative terms. So 0 does not have any negative counterpart, so we keep it as it is, and e power j into 0 will actually give 1, so we can take this out, plus summation k equal to 1 to infinity ak e power j k omega naught t minus or plus a minus k e power minus j k omega naught t. And we already saw this is nothing but ak e power j k omega naught t plus, using this result, ak star e power minus j k omega naught t. Now if we assume ak as sum bk plus jck, what do we have? X of t is a naught plus summation k equal to 1 to infinity. Let us combine the bk terms, bk into e power jk omega naught t plus e power minus jk omega naught t and plus ck jck into e power jk omega naught t minus e power minus jk omega naught t. If we just divide this by 2 and multiply by 2 and divide this by 2j and multiply it by 2j, what we have? We have a naught plus summation k equal to 1 to infinity 2 bk, and this is nothing but cos omega k omega naught t, plus you have jj, so you will get minus 2ck, right, inside the summation k equal to 1 to infinity 2ck sine k omega naught t. If you want to further simplify, you can actually replace 2bk with small bk and minus 2ck with small ck. Then you will get x of t as a naught plus summation k equal to 1 to infinity bk cos k omega naught t plus summation k equal to 1 to infinity ck sine k omega naught t. Right? So this we derived for real x of t. In general, what did we have? X of t is summation k equal to minus infinity to infinity ak e power jk omega naught t. So this is in terms of complex exponentials, and this is in terms of trigonometric sums or signals. So until now we have only seen that each of them are periodic with period t naught, and we are just adding them up and saying x of t is also periodic with period t naught. We haven't gotten into the fact that if x of t is periodic with period t naught, can it be represented by this sum, right? That we'll get into. But before that, let us see an example, in which case we'll take this x of t and see summation k equal to 1 to infinity. We say a naught goes to 0, bk goes to 0, and we'll only consider sine. So let us say it is ck sine k omega naught t, and ck, let us say it is actually 1 by k and omega naught is 1. So in that case, what do we get? Summation k equal to 1 to infinity. What do we have here? Sine kt by k, right? So let me show you in this example. It is the same, sine nx by n. So let us see what happens when we vary this. Ideally this should be infinite, but since we can't take infinite number of terms, let us see what happens when we increase the number. So initially when there is only one term, you can see the sine. You can observe just the sine wave. Let's see what happens for n equal to 2. So you can see it is superimposed. If you want to see only the second component, so this is just the sine with period, which is half of what we saw, sine x, correct? Now these both are added together, we get this waveform. Okay, so let's see what happens as we increase this. See, you can see the periodicity is maintained, correct? So somewhere here it is periodically repeated. So what happens if you go for a bigger number, 10? You can see it is approaching the ramp waveform, right? 1000. See, it almost approached the ramp waveform. So when we started with, we don't know this is going to produce us the ramp waveform. But actually when we try to put some expression for the AK and we took some sine terms and tried to add them, we are actually getting a periodic ramp or sawtooth kind of, right? This is really amazing. And if we are some way able to actually see that it is a ramp and then derive these coefficients, then it would be even greater, right? So that is what we are going to see now. Let us go back to the notes. So now our question is, given a periodic signal with period t naught, can we actually represented as the sum of complex exponentials, right? And what is the sum? This x of t is equal to summation k equal to minus infinity to infinity ak e power j k omega naught t. So now if we can find a case, correct, for that particular x of t, then we can achieve it. We can achieve this. Because this is going to be same for all the signals. Only this is going to differ. And based on what formulation this ak takes, this x of t is going to appear. Right? On the other hand, saying whatever form x of t is, that will define ak. So, if in some way we are able to find ak in terms of x of t, then this answer is yes. So, let us now try to find ak in terms of x of t. So, finding ak in terms of x of t. So in mathematics under linear algebra, this is a usual problem and usually used in finding basis vectors. Now we will use that concept and touch upon a little bit here and there, okay? So our main focus is to, let's say, find AL. We want to find AL and eliminate all other AKs. Okay, so for that what we have to do? That's the question. So I will take a simple integral. Let's first try to calculate this integral. K minus L omega naught t dt over a period t. Okay, let's say it is from 0 to t. Because we already saw it doesn't matter when we are doing a periodic integration over a period. So what happens in this case? So let us take two cases, k equal to L and k not equal to L. So when k equal to L, what happens? Integral 0 to t e power j, this becomes 0, right? 0 into omega naught t dt. And this is nothing but 1. This will give t itself. And what happens when k is not equal to L? So 0 to t e power j k minus L omega naught t dt. Okay, and this you can write it as cos k minus L omega naught t plus j sin k minus L omega naught t dt. So if you see cos k minus L omega naught t and sin k minus L omega naught t are periodic in t naught. So this is t naught, let's say. Right? Okay. Because k and L are integers. Okay. So we saw that for any k and L it is periodic and k minus L is also periodic. Right? So then what will happen? So if you integrate cos and sin over one period, you have equal amount of positive and negative and they will cancel out and integral will give us 0. So this integral is going to go to 0. So integral over one time period e power j into k minus L omega naught t dt is equal to t naught for k equal to L and 0 for k not equal to L. Now do you see where we are going? So this will actually give us only the k equal to L term and eliminate all other terms. So what we are doing is, we will take this equation x of t is equal to summation k equal to minus infinity to infinity ak e power j k omega naught t and we'll actually integrate x of t e power j L omega naught t dt. And this side also you will integrate k equal to minus infinity to infinity ak e power j k omega naught t into e power j L omega naught t dt. And here you can actually take the integral inside. So you will have minus infinity to infinity. Ak is not involved in the integral. So let's take that out. Integral t naught e power j. So it is minus, right? So we'll take minus on both sides. J k minus L omega naught t dt. Right? So this will eliminate all other k terms. Only AL will remain. And what will be the integral value? It will be t naught. And this side you have x of t e power minus j L omega naught t dt. So we want to find AL. So AL is nothing but 1 by t naught integral over 1 period x of t e power minus j L omega naught t dt. So we can now change the variable ak. It's nothing but 1 by t naught x of t e power minus j k omega naught t dt. So we actually obtained ak in terms of x of t. So this is very important. This also implies that a periodic signal with period x of t can be represented as a sum of complex exponentials. There are some constraints to it which we'll come to in the next part. But for now, we have actually obtained an expression for ak. So what did we initially start with? X of t is equal to summation k equal to minus infinity to infinity ak e power j k omega naught t. Right? So this one. So this equation is called as the synthesis equation. Why? Because we are synthesizing x of t using AKs. And this is called as the analysis equation. Because we are actually finding AK from x of t. And these AKs are actually referred to as Fourier series coefficients or spectral coefficients. Of x of t. Why spectral? Because each of these corresponds to some frequency, right? So when frequency is involved, when you're actually like representing it in terms of frequency, so it is called as spectral coefficients. These act like a weights to each of the frequencies. Okay, and generally what you have A0 as, if you substitute 0 here, it is nothing but the average of x of t itself. So this is like the DC component of x of t, right? So now let us see a simple example. Let's say x of t is equal to cos 2 omega naught t plus sin omega naught t. So now if we have to represent x of t in terms of this AKs and e power jk omega naught t, what we have to do? Since it is cos and sin, we can directly write this as e power j2 omega naught t plus e power minus j2 omega naught t by 2 plus e power j omega naught t minus e power minus j omega naught t by 2j. And also you need to observe that this is periodic with period t naught, and the fundamental frequency is nothing but 2 pi by t naught, right? They are related this way. So now it is nothing but 1 by 2j e power j omega naught t minus 1 by 2j e power minus j omega naught t plus 1 by 2 e power j2 omega naught t plus 1 by 2 e power minus j2 omega naught t. So what do you have? A minus 2 is 1 by 2. a minus 1 is minus 1 by 2j, a1 is 1 by 2j, a2 is 1 by 2, ak equal to 0 for all other k. So we can actually represent this in the graphical form. So if we have k here and ak, we plot ak. So at 0 it is 0, right? So we have 1, 2, 3, minus 3 and so on. So at 1, so since it is complex, right, we will plot the magnitude and phase separately. So magnitude wise, all are 1 by 2, right? So 1 by 2. So 1 by 2, 1 by 2, 1 by 2, 1 by 2. Let's see about the phase. So phase, what do we have? Same k. Phase of AK. 1, 2, 3, 0, minus 1, minus 2, minus 3. So minus 2 and 2, it is 0 only, right? The phase is 0. So it's 0, 0, and everywhere else also it is 0. And what about minus 1? It is minus 1 by 2j, which is nothing but j by 2. So it is plus 90 degree. And at 1, it is minus j by 2, which is nothing but minus 90 degree. Oh. So these are like sinusoidal signals continuously varying. But what about signals with discontinuities? We already had that doubt, right? So we will see that also as an example. So let us actually take this signal. So let's say it is from minus t0 by 2 to t0 by 2. And it is a square pulse kind of. So minus t1 plus t1. Let's say this is x of t. So to write it in the functional form, so x of t is 1 for mod t less than t1, 0 for t1 less than mod t less than t0 by 2. And it is periodic. So again at t0, it will be like this. Minus t0, it will again be periodic. But we are only interested in one period, right? We are integrating over one period only. So let us take only this period and try to see. So we have x of t is equal to summation k equal to minus infinity to infinity ak e power j k omega naught t, and ak is nothing but 1 by t0 integral over t0, right? X of t e power minus j k omega naught t dt, right? Okay. So now we have x of t as this. So ak is nothing but 1 by t0, and the integral will be from minus t1 to t1. So minus t1 to t1. X of t is 1 in that region, right? So we have 1 e power minus jk omega naught t dt. So what will we get? Integrating this, we will get minus jk omega naught t by minus jk omega naught from minus t1 to t1. So this is nothing but 1 by t0 e power jk omega naught t1 minus e power minus jk omega naught t1 by minus jk omega naught. Alright. So this we can write it in sine form. So it is nothing but 2j sine k omega naught t1 by minus jk omega naught. I think here I missed the minus sign, correct? So this will be plus. So now j and j cancels. Omega naught t naught is nothing but 2 pi. So what do we get? We get sine of k omega naught t1 by pi k. So you can see this value is not defined for k equal to 0 because the denominator tends to 0, then the whole term may tend to infinity. This is for k not equal to 0. For k equal to 0, we can find separately because it is just the average of x of t. So average of x of t over this interval will be 2t1 by the total time period. which is nothing but t naught. So what it means, if you actually substitute these terms in this expression, you will actually get this x of t. So this can be actually represented in the Desmos calculator. I will show it, but before that I'll also give an intuition of how this works. So, or maybe I'll first show you that. So this q is nothing but the number of coefficients we're considering at the time. So this is just one coefficient, which is just the omega naught t, fundamental thing. This is considering the first and the second frequency, and 3, 4, and so on. So you can actually see the circle here. I'll say you what this is, but you can see as the number of coefficient increases, the waveform actually approaches the square wave, correct? If I just increase this to 1000. So now you can see the wave actually tends to being the square wave, right? Also you should observe other thing, correct? You can see these spikes, right, never disappears even when I increase the number. See, they only become smaller in width, but the height is not changing, not reducing. So we'll come back to that later. But for now, you observe this and let me say you what those circles represent. So what this A naught represents. So let's say this is the y-axis. So now we are, let's say, plotting the vertical displacement. So you take the first Fourier coefficient and then you place it accordingly. So this is A naught, meaning you place A naught here. Okay. And then A1, you take the second or A1 Fourier coefficient. So this is in terms of trigonometric sums. So this A1 corresponds to trigonometric sum. Because here A minus K is nothing but equal to AK. Right? If you do this, only then the cosine terms will remain. So what you do, if A1 is, let's say 1, you draw a circle of 1 unit. And then take A2. With this point on circle as center, you draw, if A2 is half, you draw another circle of radius half. And you repeat this. Again, a point on this, you draw another circle with coefficient A3 as the radius. And so on you continue. And what is happening? This sine or cos omega naught t is nothing but the vertical displacement, correct? When this is moving with a velocity of omega naught, the vertical displacement is actually represented by, given by sine or cos. So the same thing here, and we are stacking one upon the other. So it is similar to adding them. So here you will actually get the waveform based on the coefficients. So that is what is being represented here. So you can actually see the waves moving. Since it is such a big number, it is taking time because of bigger computation. Let's go with a smaller one. So you can see the motion of the circle. So how beautiful analogy, right? So there are so many simulators available online. You can search and find them, and I would recommend you to try and see these kind of things. It gives an intuitive feels and also makes the subject interesting. So now let us go back to our notes. So we'll continue where we left. So now let us discuss the convergence of Fourier series. So this addresses the question that whether all periodic signals can be represented by the Fourier series. We already saw in the historical past, Lagrange actually did not agree to discontinuous functions being represented by sum of smooth signals. But we also saw in the previous example that they do have form, we have found the AK corresponding to the discontinuous signals, and we'll see what's the catch. So basically what we do, so we have x of t as some signal, and now we are representing x of t in terms of summation k equal to minus infinity to infinity ak e power j k omega naught t, right? So let us say, let's only consider some finite number of terms. Let's say from minus n to n, ak e power j k omega naught t. And let us compare this finite number to xn of t. And we actually find the error between these two, right? So we give it as x of t minus x cap n of t. And this again depends on n. So if we actually say this is a very good approximation of x of t, then what we also need is the energy in the error signal should go to 0. Energy in the error signal should go to 0. This is one way of seeing whether if this Fourier series is actually a good representation of this x of t periodic signal. So what is the energy in the error signal? Let's say it is En. So it is nothing but integral over one period. Since these are all periodic signal, we are only considering the integral over one period. So, and it is nothing but En of t mod square dt. So if this En actually tends to 0 as n tends to infinity, then we can say Fourier series is a good approximation. It is actually approaching x of t in the limit n tends to infinity. Approximation of x of t. So there are again mathematical tools developed to find actually the optimum value for En. So to put it in a simple way, let's say En has a minima which is 0. Then we know how to approach. If we just divide En by the coefficients and equate it to 0, we can find a solution. And let's see what is that optimum solution is. Okay. So we have En of t as this. So En of t is nothing but mod x of t minus summation k equal to minus n to n ak e power j k omega naught t, right? And now we need to find the energy. So mod En of t whole square. So you can just take the complex conjugates and multiply. So summation a equal to minus n to n ak e power j k omega naught t, this into the complex conjugate of that. That will give you the absolute value square, right? X star of t minus summation k equal to minus n to n ak star e power minus jk omega naught t. And then En will be nothing but this taken together and integrating with t naught, right? T naught into dt. And we have to actually divide this by the coefficients, the derivative we have to find. But observe that AKs are complex. We cannot directly take the derivative of complex numbers because AK and AK star are there. The complex conjugate are also applying. So what we'll instead approach is, we'll actually take AK as BK plus JCK. Okay, then we'll actually take derivative with respect to BKs and CKs. Okay, so let's do that. So we have this one. So this is nothing but bk plus jck, and this is again bk minus jck. Now let us take the derivative of bl. Okay. So in the first thing, only the bl term will remain, the coefficient of bl term, which is nothing but minus e power jl omega naught t. All others will be 0. And you will be left with summation k equal to minus n to n bk minus jck e power minus jk omega naught t dt. And in the second case, when you keep this constant and take this derivative, what will you obtain? So plus integral t naught x of t minus summation k equal to minus n to 1 bk plus jck e power jk omega naught t, right? And here we will have minus e power minus j l omega naught t. Correct? Okay. So then what do you have? Integral over t naught x star of t minus e power j l omega naught t, and this one is nothing but plus integral summation you can take outside k equal to minus n to n bk minus jck integral e power j l omega naught t e power minus jk omega naught t dt. So this integral only L equal to K or K equal to L terms will survive, right? So we'll simplify it in the next step, but let's also write this out. X of t minus term is there, so minus e power minus JL omega naught t plus summation K equal to minus n to n bk plus jck integral t naught e power jk omega naught t e power minus jl omega naught t, and there is again a minus term. Sorry, minus and minus will become plus t. Here again only k equal to l terms will remain. Right? So what are the terms remaining? bl minus jcl and bk plus jcl. So this and this will cancel, you will get 2bk. So this is equal to minus integral t naught x star of t e power jl omega naught t plus 2bl, this is bl, plus on minus integral t naught x of t e power minus jl omega naught t dt. So your dt comes. Okay. So next we'll take the derivative of En with respect to Cl. So what will we obtain? So between Bk and Cl, Bl and Cl, what is the difference? In this term, you will actually have a J term, and in this term, you will actually have a plus J term. Because it is minus J into minus, it will be plus J. Here it is just minus J. So let's try to write it out directly. So you will have J minus J integral x star of t e power jl omega naught t dt, and here what will you have? So minus j into minus will be plus j into minus j will be minus of minus 1, which is 1. So we'll have plus ck, or let us write it fully, minus j into minus of bk minus jck. So plus j into bl, because this term will go away, minus jcl, and what is we have here? We have plus j into this term. So plus j integral x of t e power minus j n omega naught t dt, and then we have plus j into minus. So minus j into bl plus jcl. So what will this be? This will turn out to be jbl plus cl, and this is minus jbl plus cl. So minus jbl cancels. So what we have? Minus j integral x star of t e power jl omega naught t dt plus 2cl plus j integral this all with respect to t naught x of t e power minus j L omega naught t dt. Okay. So each of these will be equal to 0 to get the optimum. Right? So now we can try to relate these both terms. Let's say somehow we want to find AL. AL is nothing but BL plus JCL. So we have BL term here, CL term here. So we'll multiply this with, so let's say this is equation 1, equation 2, 1 plus j into 2. So what will this be equal to? So if you can see, this one will remain same. Copy, paste. So this is same. J into the second. So j into minus j will be plus. So plus x star of t e power j L omega naught t plus 2jCl. And here you will get minus integral t naught x of t e power minus j L omega naught t dt. So you can see this and this term cancels, right? And this is equal to 0. So this side you have 2 into BL plus JCL is equal to, these two are same. So 2 integral T naught x of t e power minus JL omega naught t dt. And I think we missed one term while integrating. So this integral, right? So this integral is actually equal to T naught, correct? So we'll get a T naught term here. So T naught and T naught here. So we'll actually get T naught what? So 2 T naught. So BL plus JCL is nothing but AL. So what is AL? It's nothing but 1 by T naught integral T naught x of t e power minus JL omega naught t dt. So what is this? This is nothing but the synthesis equation, right? AK is 1 by T naught x of t e power minus jk omega naught t dt. This is the synthesis equation, or the analysis equation, analysis equation. So we actually started out by wanting to find the optimal solution for xn of t representation in terms of the sum of complex exponential, and we wanted to find what coefficients are best suited. And we approached it mathematically, and we actually found that these are nothing but the Fourier coefficients we actually normally obtained before. So from this we can actually conclude that the Fourier series representation is a good approximation for x of t. And also in the limiting case, when n tends to infinity, it can fully represent the periodic signal x of t. But there are some conditions to it. There are some conditions. So one thing you can observe that AKs should be finite, correct? We can't have infinite AK. So what it also implies? It implies mod integral x of t e power minus jk omega naught t dt 1 by T naught, right? This should be finite. This integral should be finite. And in general, the energy of x of t should be finite. So x of t should be a finite energy signal. So integral mod x of t whole square dt over one period should be finite. And the other thing you can see is for discontinuous signals. So x of t, xn of t may not converge to x of t for all t, especially in the discontinuity, as we already saw an example, right? You can think about it. So there are certain conditions developed by Dirichlet called as Dirichlet conditions for a periodic signal to have a Fourier representation. So the first condition is what we actually saw here. The x of t should be absolutely integrable. Why this is the case? We want ak to be finite. But we also see ak is less than or equal to mod ak less than or equal to is equal to mod integral t naught x of t e power minus j k omega naught t dt. And we can take the absolute thing inside. So we have x of t e power minus j k omega naught t dt. So this is less than or equal to, because we are taking inside the integral, right? And this again less than or equal to t naught x of t into mod of this. But mod of this is nothing but 1. So it's nothing but x of t dt. So this implies that x of t should be absolutely integrable. So this is the first condition. As an example of a signal which violates this, if you consider x of t equal to 1 by t for 0 less than or t less than or equal to 1, and it's periodically repeated. So how it will actually be is 0, 1, 2, 3. It will be like this. Right? It will be like this and repeat itself. So you can see that the integral of this 1 by t dt actually tends to infinity and it does not converge. So signals like these will not have a Fourier series representation. So this is condition 1. So the second condition, x of t should have bounded variation in a finite interval of time. That is, it should have finite number of maximas and minimas. For example, let me give you an example where this is violated. X of t is equal to sine of 2 pi by t for 0 less than t less than or equal to 1. So you can see 1 by t actually goes from 1 to infinity, correct? So x of t will actually, sine of this number will actually have infinite number of variation. It will be something like this, and again it will repeat the same. And this side also it is the same. So you can see there will be infinite number of maximas and minimas. So such signals can also not have a Fourier series representation. And there is a third condition. So there should be only finite number of discontinuities in finite time interval. So if you take the square pulse, square waveform, so it has lots of discontinuities over an infinite period of time. It has infinite number of discontinuities. But if you consider a signal like this, let's say 0 to 1, it starts from 1 and for every, and let's say half, and it reduces by half. So the height and width is halved every time. So next it will actually go to, it will have a height of 1 by 4 and width of 1 by 4. Then 1 by 8, 1 by 8. So it will have infinite number of discontinuities. So although these kind of signals are not possible in nature, so these class of signals also exist, and actually they do not have a Fourier series representation. But these are only some limited class of signals. So it also means that large class of periodic signals can be represented by Fourier series. And all our interested signals can be represented by Fourier series. Large class of periodic signals can be represented by Fourier series. And before I end this lecture, I want to give a small insight on what is called as the Gibbs phenomenon. We actually saw this in this class. So we actually observed the square waveform when we represented it using finite number of terms, right? It actually observed like this. But as it goes and goes, we actually saw some spikes, correct? Even as n tend to large number, the spike never disappeared. Yes, we saw that, right? So, Gibbs formulated that the height of the spike had a maximum of 9% of the height of the signal, even as n tend to be larger. So what is actually happening? This is Fourier series failing here. No, what is actually happening is, as n increases, the height is remaining same, but the width actually tends to 0 as n tends to infinity. So if you see, initially the width here was high, and here you can see it is actually very small, and when n actually tends to infinity, this will actually disappear. But even though the height is like 9%, the width is actually disappearing, which implies that the error signal, so the energy in the error signal is actually tending to 0. The energy in the spike will also tend to 0 as n tends to infinity. So it is normal for you to observe the spikes at the place of discontinuity. So you can see there is a discontinuity here, and you can observe the spike. And the other thing is, at the point of discontinuity, the value of xn of t as n tends to infinity, right? This is nothing but the concatenated Fourier series representation. This average of x of t from both sides. For example, in this case itself, let's take this case. Let's say this value is 0 and this value is 1. So at this point, let's say t1, minus t1 and t1. So at x of minus t1, it is actually average of x of minus t1 plus x of minus t1 minus by 2. So minus t1 plus is nothing but 1 plus 0 by 2. So it is 0.5. So at this point, if you have to represent it with some large number of Fourier series coefficient, it will actually be 0.5. And at every other place, x of t will approach limit n tends to 0 infinity xn of t for all other t. So in general, For continuous signals which does not have any discontinuity, x n of t limit n tends to infinity actually approaches x of t for all t. So I believe I covered a lot of new topics for you in this lecture, and I would urge you to maybe go through the lecture once again if required for you, and also it would be good if you read it from the book also once. Okay, enjoy your learning guys. Take care. Bye.